the conclusion of the derivatives introduction, I guess. Because the next few units are all going to be about what they're used for and what we can do with them and undo them and all kinds of stuff like that. So given a function f of x, the derivative, f prime of x is known as the first derivative. The second derivative would be the derivative of the first derivative. How about that? It's interesting, right? And we would denote the second derivative as f double prime of x, which is what you're seeing right there. So you can say f double prime, y double prime, or this really weird setup, d squared y over dx squared. I'm going to stick with f double prime. Okay. I will stick with f double prime.
What is the usefulness of d squared y dx squared?
Okay. So you know dy dx means derivative of y with respect to x. Okay, that's what that means. The dx part means delta in x or insanely small change in x. We just use d to represent the delta. But the d that's on top of the fraction is not so much a delta. It's something slightly different, has like a different meaning. This symbol, the way it's set up, is highly abstract and, to be honest with you, hard to even describe why it is the way it is. Why not dy squared over dx squared? Or for d squared y, why not d squared x, right? There was a paper, was it either, I think it might have been released at the beginning of last year or the end of the year before, talking about a better assemblage for this that means something more in mathematics, but it hasn't made its way into mainstream mathematics yet. Basically, what I'm getting at is I don't know. Because it's a highly abstract idea. As long as you know that it means second derivative, you're set, okay? Because that's all I know it to mean. I know it means more, but in a weird way. Because it doesn't mean dy dx times dy dx. It's just the weirdest stinking thing, man. I was afraid someone was going to ask. Okay, so f prime of x is this. We've been told to find the second derivative. That just means the derivative of the derivative. Before I go ahead and do this, because this is rather simple, before I go do this, I would like to at least talk about what it means to be the second derivative of something. If the first derivative is the slopes, then the second derivative is the slopes of the slopes. For example, let's just say you have the standard cubic. Its derivative function, its gradient function, is a quadratic. That means that any slope of a cubic can be found by plugging in an x into a quadratic. And you will get a number that is either positive, it'll always be positive, assuming it's a positive cubic, right? Because it would be a...
The cube is the one that goes up.
Yeah, but it has all positive slopes, though.
Oh, okay.
Yes? Okay with that?
I don't know.
Well, how about Desmos to the rescue?
An x cube goes down.
How about Desmos to the rescue?
Okay.
Instead of talking about it, we'll just look at it.
Oh, because it's always going up from left to right.
How about instead of talking about it, we just look at it?
Okay, you're right now.
He just doesn't shut up, does he?
No, I understand now. You don't
Fantastic! Desmos to the rescue. So x to the third. This is a standard cubic. I'm just going to adjust my picture here, and I want my x-axis to go a little bit teensier, so that way I can... There. Okay, so we've got a standard cubic. This is the parent cubic. Its gradient function is 3x squared. The y values of that blue curve represent slopes of the red curve. For example, at x equals 1, the y value of the blue curve is a 3. What that means is the slope of the red curve is 3 at x equals 1. So the y values of this blue curve represent slopes of corresponding x values of the red curve. But the Second derivative would be 6x. The y values of the purple, let's call it a curve. I know it's a straight line, but technically all polynomials can be classified as curves. The y values of the purple curve are slopes of the blue curve. Okay? That's what's happening here. And if you look, don't pay attention. In fact, I'll just turn it off, and I'll turn this off. Right here at 0, 0 is where the parabola begins to have positive slopes. That is why that straight line is above the x-axis there, because that's where you have positive y values. The slopes on this side are all negative, which would give our purple line negative y values, which is why it's down here. So that's what the second derivative represents. It's the slopes of the slope function. Cool? At least with the idea for now. We'll get into the geometry of it more in the upcoming unit.
Why?
Anyway, do you understand what I'm saying? And we'll get into the geometry more of it in the next unit.
Yes.
Awesome.
Does that mean like why?
All right. So just for the mathematics, before I find this even first derivative, I want to rewrite this thing. I want to write it as x to the third minus 3x to the negative 1. So first derivative is, and I mean just basically do little spot derivatives of polynomial stuff. Anyway, bring the 3 down. You got 3x squared. Bring the negative 1 down to the negative 3. Now you have a positive 3, but the exponent needs to decrease by 1 down to a negative 2. There's your first derivative. But we need to find our second derivative. That's what we were asked to find. Okay, well. Now you just take spot derivatives here. Bring this 2 down to the 3. Now you have a 6. Drop this exponent by 1. And then you're going to bring this negative 2 down to the positive 3. And now we have negative 6. Dropping this thing's exponent by 1 gets us to a negative 3. Now obviously I didn't need to write this one, but there it is. We don't want to leave it with negative exponents because that's not the way it was given to us. So no negative exponents. We have 6x minus 6 over x to the third. Whoop. And are there higher derivatives? Of course there are. I could find the derivative of this, and then the derivative of that, and the derivative of that, and so on and so forth. Now, this thing out here in the front, this standard polynomial, eventually it just goes to 0, and then it stays at 0. But this would not, would it? This would continue to oscillate between positive, negative, positive, negative, positive, negative. And this exponent would continue to increase by 1. And then this would continue to get multiplied by the new power. So this would go to 24, and then to 120, and then to 720, and then to 960, so on and so forth, while this went positive, negative, positive, negative, positive, negative. And it's just really interesting because you could almost set up a sequence of derivatives if we wanted to, he said with a slightly raised voice. Anyway.
What's that mean? What's that mean?
Part B.
Okay.
Again, I don't want to have to deal with that 1 over x, so I am going to rewrite it as x to the negative 1. This is going to be an interesting question, because just finding the first derivative is going to require a product rule.
Oh crap, I forgot about that. That's so stupid that you have to do
So u is x, and v is cosine x. And of course is the product rule, u prime v plus uv prime.
Is it negative sign? No, it's negative.
U prime is 1. The derivative of cosine is negative sine. Our first derivative then, and I will simplify it a little bit because I have to find the derivative of that. So we want it to be as simplistic as possible. Our first derivative will be u prime v plus uv prime. Now that was just this part, but we do still have to have the derivative of x to the negative 1. Bring the negative 1 down to the front, drop the exponent by 1. Wow, it doesn't really clean up much, does it? That's unfortunate. So we're going to get cosine x, and you know what I'm going to do? I'm going to keep it like this, just for a moment. I just chose to put the minus on the x, that way because I'm going to have to do a product rule. This way my u prime was simple, instead of having to worry about a negative in my v prime, okay? So yeah, I didn't really do anything to this. So why did I do that? I did this because this is going to require, when we go to find our second derivative, another product rule. However, if you had just put this minus sign in front of this x, there's a chance that you might have forgotten that that minus sign belonged to that x in your product rule. And that's the only reason why I chose to leave it like this, to guarantee that I don't mess up my product rule. For this new product rule, again, u prime v plus uv prime, yeah, and I left it like this instead of just writing. If I had just written negative x sine x, then there's a chance that people would have tried to do the product rule with x sine x, forgetting that that negative sign belonged to the x. Yeah, so that's why if you leave it like this, you go, oh, u is negative x. I wrote 1. Negative x. V is sine x. U prime is negative 1. V prime is cosine x. And we might as well be super colorful. F double prime of x. Well, first I have to take the derivative here at cosine. The derivative of cosine x is negative sine of x. Now, my product rule. So plus u prime v plus u v prime. And then all the way at the end, the derivative of this. Bring the negative 2 down, you have a positive 2. And decrease the exponent gets me to there. And it's only going to clean up a little bit, to be honest with you. As in, these two are like terms. This is negative sine of x, and so is this. That's really the only thing I see that's really going to be pretty. So this is negative sine x minus sine x. I have negative 2 sine x minus x cosine x plus 2 over x to the third, because we don't want negative exponents. Yuck. No, I just try to. But sometimes the questions will say show that the derivative is this, or sometimes you'll have to plug something into it, and it would be, especially if you're evaluating trig, it would just be easier if you had one less trig to worry about. But no, not really. At least it's colorful. Everybody got it? Yes. Wait, was that all the notes?
No.
Oh. Oh, yeah, when I'm finished with the notes, I'll be happy to do some more questions. That's a fantastic use of extra time.
Okay.
So yeah, there are more derivatives. There's actually as many derivatives as I want. 50th derivative, 100th derivative.
Would it just be constant after like?
No, it wouldn't be. Now, if it was a standard polynomial, then yes, you would reach a point where your derivative was nothing but 0. However, like I was just showing you, come back to the front,
The
like
other one would be instant.
this goes on forever.
Wow. Oh, because it's negative.
Because as a negative exponent, it just keeps getting bigger and bigger and bigger down here. Another kind of derivative that will go on and on and on are radicals. You're never going to get 0 out of that because you can always subtract 1. So yeah, so radicals do the same thing. Yes, Bria?
Why are derivatives used? Like, where are they used like in the real world?
They're rates of change, slopes. That's what the derivative means.
So what do you, like, why would you find the second derivative?
The second derivative, are you in physics? Well, if I told you that well, this jumps ahead a little bit, but if you're driving somewhere, okay? Let's just pretend you're driving in a straight line. And we can plot your position over time. Cool with that? But what can we do if we have two positions with two times and try to connect them?
Oh,
We could find how fast you were going, right?
yeah.
Now that would be the slope. So velocity is the derivative of your position. And the rate of change at which your velocity changes is known as acceleration, right? Derivative of velocity is acceleration. And if we know what your speed was and we know how long you were driving, couldn't we actually figure out how far you drove? Yeah?
Remember that old test question?
I'm just asking. We could, right? Yeah. That's what happens when you undo a derivative in mathematics. So yeah, they have a lot of real world applications. Anywho, the nth derivative of y with respect to x is obtained by differentiating n times, just as many as you want. And we would use this notation. It's in parentheses. So after you get past the second or third derivative, you pretty much stop using Roman numerals. Instead of going for 4, like let's say the fourth derivative, you wouldn't do f with an IV notation. Fourth derivative would be f with a little 4 inside those parentheses. And you must use the parentheses. If you don't use the parentheses, you're describing something else in mathematics. Everybody clear with that? Okay. And again, what the heck does this mean? I did my best to even understand the paper I was reading. Like that's how high it was, and I was still like, yo, I don't know.
Have you looked at Aiden's math IA?
Aiden's not my student.
I know, but you should read this. This is about how like he literally did his IA on the shape of the universe.
I know.
And used two-dimensional geometry. It's crazy. Like I was trying to read it, and I literally he was using stuff that you would know, but he was applying it like in ways that I was like, eh.
Okay.
It was crazy.
You're assuming that his mathematics is correct.
Yeah.
Because it just sounds so smart.
Because it sounds
I
smart.
don't know if it's correct or not.
Yeah, anyway.
I don't know.
I'm
how.
telling you that f of x is, and that's another one that'll go on forever, trig, because they just oscillate through each other. So yeah. So I'm telling you that f of x is cosine 2x. We are going to show that when we plug in pi over 8 to the third derivative, we will get 4 root 2. Well, obviously, we're going to have to track down the third derivative. And the derivative of cosine of 2x is going to require the chain rule because its argument is a function. I'm going to attempt to do this all in one color, but if need be, I'll switch up colors afterwards. F prime of x. The derivative of cosine of some stuff is negative sine of that stuff times the derivative of that stuff. This is the chain rule, right? So now I'm multiplying by 2. Alberto asked, is there a reason to clean it up? Well, yeah, I'm going to want to clean this up because I have to find a couple more derivatives of it.
Oh, wait.
What's up?
Do you not have to use the rule?
I'm sorry?
Wait.
Yeah, this is the chain rule right here.
Oh, okay.
The derivative of 2x is just 2. So it's derivative of outside, don't change the inside, times the derivative of the inside. This is going to give me negative 2 sine of 2x. My second derivative will be the derivatives of this. Again, more chain rule stuff. This constant in the front, the negative 2, is going to come along for the ride. It's unaffected. So we have a negative 2. The derivative of sine of some stuff is cosine of some stuff times the derivative of that stuff. that cleans up to negative 4 cosine of 2x.
Wait, doesn't it just? So wouldn't it just be going back and forth?
Sine and cosine oscillate between each other and change symbol at the same time. Sine goes to cosine, cosine goes to negative sine goes to negative
So it's
cosine,
just-
negative cosine goes to sine.
So it's just like there's an x, like every time that you would like go to the next derivative, it's just x in front of that to a power, and then you just change the sign.
But it's not a power though. It's a I don't know. It's hard to describe. I'm not really sure what you were saying. Now I could have done 3 tick marks, but they represented it as a 3 to avoid confusion, I'm assuming. So we might as well do that as well. The negative 4 comes along for the ride. The derivative of cosine of some stuff is negative sine of some stuff. Of course, we have to do the chain rule and multiply by the derivative of said stuff, which again will be a 2. So at last, this thing cleans up. The 2 negatives cancel, and we have 4 times 2 in the front. We have 8 sine of 2x. That is our third derivative. That's the third derivative. What we need to do is substitute in pi over 8 as our x value. And this is where trig takes a drastic turn left for a lot of people, when you have to plug something in and actually evaluate some trigonometry. Third derivative of f of x evaluated at pi over 8 is 8 sine of 2 times pi over 8. Well, 2 over 8 reduces, doesn't it?
Wait, what?
That's the only way this would be, like, this would happen, right? It, like, we took some test if it would reduce, like,
In this course, yes.
Okay. In
the advanced pre-calc class, no, I could force them to use half-angle identities and things like that, if you recall back to those
good old days.
post-traumatic days.
Right.
You never know, though. They might be butts and make you use a double angle identity here, which is considered fair game. But if you double an eighth, you get a fourth. So this is 8 sine of pi over 4. And I guess this is what makes trig hard for most people, is not memorizing the 2 special right triangles.
Wait, why?
There are only 2 special right triangles that you need to be aware of. The 45-45-90 triangle and the 30-60-90 triangle.
Why did
Yes, there are. Anyone with a 15-degree angle is also special, and anything with a 22.5-degree angle is also special.
Why did it go to 4 instead of 6? I'm confused.
Why did what go to 4, Gavin?
Why is it pi over 4?
What
not
is
like
2 over 8?
4, but
You mean 1 over 4?
what like you can't like what with the pi? But there's
Yeah,
a
so if
pi.
I gave you 2 pies, and 8 of you had
Okay,
to...
but it's a number. That's like saying like 2 times 3 over 8, and you reduced it to just 3 over 4.
That is exactly 3 over 4, Gavin. 2 times 3 is 6, and 6 over 8 is 3 over 4.
Oh, okay. Okay, oops, I did that. Oopsies, okay. Alright, you can continue now.
Okay. I'm glad that made it onto video evidence. All right.
Well, because it's weird, because pi's like 3.1.
In case I ever need, defense as to why my actions were what they were in court, I could be like, well, I mean, did you not hear the statements? Okay, so sine of pi over 4. Look, pi represents 180 degrees. 180 divided by 4 is 45. So this is a 45-degree angle. This is quadrant 1, beginning at 0 and going up to 90 degrees, which is also pi over 2, but whatever. Going to draw a generic triangle, picture not drawn to scale. Like I said, pi over 4 radians is 45 degrees. So I could put a 45-degree angle right here. This must be a right triangle All triangles add up to 180.
45.
That means this angle up here is 45 degrees as well. Now check this out. This triangle has two equal angles. What kind of triangle is it then, by definition?
Isosceles.
Isosceles. That means these two sides are equal to each other, aren't they? Great. So what we're going to do is we are going to assign a value to them. It doesn't matter what value you give them.
4.
So I'm going to give it a value of 1 to keep the numbers nice and small.
Root.
And if you could do Pythagorean theorem, 1 squared plus 1 squared
2
is
squared.
2. 1 squared plus 1 squared is 2, which means that the hypotenuse is the square root of 2. Tell you what, I'll just go ahead and show that math because it didn't sound very good in the room. 1 squared plus 1 squared equals c squared. That means 1 plus 1 is c squared. So c squared is 2.
Oh.
Take the square root of both sides. Hypotenuse has a length of root 2. There we go.
Wait, isn't that a triangle?
Okay.
Okay.
And then 30, 60, 90.
Just verifying.
Okay.
Slap the gay out.
Okay.
You just see like another person from my dog.
SOHCAHTOA, sine, cosine, tangent.
So cut. So
Sine uses the opposite side and the hypotenuse. We are here. You're always at the angle that's at the origin, nowhere else. So from here,
put 1.
it is not 1.
Oh, it's up there for hypotenuse.
What we have is 8 times opposite over hypotenuse. That's 8 over root 2. That's not what we were supposed to have found. But why would you do that? You mean you would rationalize the denominator? You don't want to have square roots in the bottom of a fraction. So you rationalize the denominator because root 2 times root 2 is no longer a square root, is it?
It's just 2.
Root 2 times root 2 is just 2.
Yay.
What we have here is 8 root 2 over 2. And 8 divided by 2 is 4. And that is where our 4 root 2 comes from.
Well, that was actually cool.
Any more statements about multiplying numbers, Gavin? Before I hit stop, I just want to make sure we get it on evidence.
You don't have to.